Okay, welcome everyone. This is Mr. Allen. Today I'm going to try to review what we've seen so far and what you should have pulled out of the investigations. Ministry expectations are that you do investigations, and the idea is that that's a better learning opportunity for you than just kind of watching and listening to somebody else do the work. But the nice thing is, if you did miss something, then hopefully we can cover it in a summary like this one. So I've highlighted a couple of key terms here for our purposes. Degree, again, was something we saw in one of the earlier sections. The degree of a function, or a function or any polynomial. If we have something that looks like this, that's a 4, by the way. We have the degree of the function is always the highest power. So whatever else I have here, my degree is always established by what's my highest exponent. In this case, this would be a quartic or a fourth power function. Obviously, if 3 is the highest number, that's cubic, and so on. So what that does is it allows us to sort of have a good idea of what our graph's going to look like. So in grade 10, I could even go back slightly further, I suppose, and say in grade 9, oh, it's not going to let me say in grade 9, there we go. In grade 9, everything you did was straight line. And so we never talked about it, but the degree of an expression like this one is a first degree, and a first degree is a straight line. Essentially the graph just goes up and up and up, or straight across, or down. In grade 10 and again in grade 11, you started to see quadratic functions, and those were second powers, although again maybe didn't use the word degree at that point. X squared goes down, comes back up. The key here is to recognize I have in a second power expression, we have one change of direction. I have this part that's decreasing and then this part that's increasing. In yesterday's investigation, we started to look at what happens when we have things in factored form. And again, you saw this one in grade 10. You have two expressions here, or sorry, two terms here multiplied. And although I can't necessarily see it, at that point right there, where I'm crossing the x-axis, I have the point -4, 0. And of course over here I have the point 2, 0 established from our factored form. Okay, so this is the factored form of a quadratic expression, and what we got into yesterday was the quadratic forms of other expressions. So as we go through these, the cubic function has a basic shape of this. Starts down in the negatives, comes up, crosses at 0, and then continues on up this way. One of the things you'll see written down in some of the questions is discussion of end behavior. The end behavior is always just asking you what's going on as my graph continues on out over further and further. So in this case, as the x values get larger, I mean they're fairly small here, but as they continue to get larger, my y values will continue to get larger as well. And so what we tend to write for end behavior there is, and this is just again kind of a note because I couldn't mark up the other page, is essentially as x tends to infinity, and this is just kind of notation saying as x approaches infinity, or x gets bigger and bigger as it goes out that way as far as it can go, the y values also go up and up and up. So this is sort of just, and we'll see this a lot, so don't worry too much if it looks kind of odd to you, but this is what we're talking about when we talk about end behavior. As our x values continue to get larger, our y values do as well. Going the other way on that same graph we just looked at, as the x values go this way, go negative, -2, -3, -4, and so on, our y values get smaller and smaller and smaller, or they get to be bigger numbers but negative. You can sort of see that down here I've got -500 and so on, and so my end behavior in that case is as x goes towards negative infinity, our y values tend towards negative infinity as well. And so really all you're looking for there is, when I look at my expression, can I figure out, am I going up and up and up and up, or down and down and down and down in each direction? Now what do I want to do here? Let's zoom back in. And for those of you who are new, this is a program called Desmos. I'll refer to it and use it fairly often, and you will too. It's a nice way for you to check things. It's kind of like a built-in graphing calculator, and quite a bit nicer than I think most graphing calculators. If you have one, obviously that's fine, but I like the nice big screen. On your phone, you'll probably have something that's decent. But if you get stuck with things, you can always kind of flip back in here and say, what should that graph look like? Get an idea of what you should be seeing. So if I look at a second one here, again, following the factored form here, I should have put these in a different order, but I have x plus 4, and I have a 0 at negative 4. I have x minus 2, and I have a 0 at 2, and of course I have a 0 at 1 as well because of the x minus 1. So that's sort of the first thing you'll recognize is, regardless of the size of our graph, or the degree of our graph, our in factored form, these are the zeros. And so I can kind of know that those points will be there. And then if I have a basic idea of what my graph does, I'll have a pretty good idea what it looks like. So again, right off the bat, I see that there are 1, 2, 3 x values. So if I multiplied this out, it will be cubic. I know then that it's going to start down here and kind of come up somehow and hit that point. At this point, I don't know if it goes this high, if it goes way up off the screen, and so on. That's not of a concern for us right now. What I'm interested in is the fact that it's going to hit this spot. It's going to come down through that spot. We'll discuss that in a second. And then it's going to hit these two spots. Again, it will drop to a certain point here. I don't know what that point is. Doesn't really matter at this point in time. So the only thing we haven't said then is, how do I know this point? And what you want to remember is the factored form of an expression, it means, like, this is telling me to multiply these things out. I'm not going to do that, and certainly when I get up to the 5th power and so on, I don't want to do that. But if I did expand this, and certainly and we all know we can do it, the last number, the constant on the end, is going to be obtained by multiplying negative 2 times 4 times negative 1, which is positive 8. And so the y value, the y-intercept, we get by multiplying the numbers out. The degree of the function we get by just sort of recognizing how many x's do we have if we did multiply it out. We have an x times another x times another x. So I have a cubic function. It will cross at negative 4, positive 2, positive 1, and we'll hit the y-intercept at positive 8. I don't know why I had this one on here. Oh yeah, I do. We'll see it in a bit. Okay, so continuing on, 4th power expression. This is the basic shape. This is the x to the 4. It looks kind of like a quadratic expression, except we have what looks like a flat bottom. It turns out, of course, it's not really flat, and if I zoom in a lot, it's sort of, you get some really small numbers in here. There's 0 0.0, 0 0.001. It shows a few here that look like they're zeros, but in fact they're just zeros with more decimal places out there that aren't showing up. And you can sort of think about that. If I put 0.001 to the exponent 4 into a calculator, I get 0.000000000000001, something like that. Not exactly 0, except at that point specifically, but the other numbers that are around it are very close. If we extend this out a little bit then, and I've got the part here cut off, but so my factors, and again, based on what we saw before, this new factor that I've added onto the last graph, x plus 6, means I'll have a 0 at negative 6, 0. The others are exactly as they were. Positive 2, negative 4, positive 1. Negative 4, positive 1, positive 2. And then the same argument right here, I've got the number 48 as my y-intercept. And if I multiplied, well, we already knew that negative 2 times 4 is negative 8, times negative 1 is positive 8, times 6 is 48. And then again, stress that these other points I don't know, but what I do know is I have a fourth power expression. It will have the basic kind of a W shape or a flat bottomed W if it's just the basic x to the fourth. And so my graph's going to come down, hit negative 6, come down here to a certain point, then come back up, pass through negative 4, and so on. And our fifth power, last one, looks a lot like the cubic with the flattened bottom. So again, it extends the cubic the same way that the fourth power extended our parabolas. If we do add in again, the 5 shapes, everything is exactly as it was. So now I'm starting from my basic shape, which is down here and coming up through my 0 point in this case. I've got the new one I'm going to hit at all the regular points. The negative 6, negative 3, negative 1, positive 2, positive 5. Again, it's the value that makes each of these things equal to 0. So negative 6 into here would make a big thing, the whole thing multiply out to 0. Negative 3 in here makes this whole thing multiply out to 0. And then the last point is the 180, the y-intercept, and again 6 times 3 is 18, times 1 is still 18, times negative 2 is negative 36, times negative 5 is 180. Okay, so we're going to go back. I thought of something a moment ago and maybe we'll run into it again. Some terminology here, roots, zeros, all the same thing. So as they were again in grade 10, grade 11, we talk about roots, we're talking about where does y equal 0. And so that's kind of the simple thing here. We're interested in where do I hit the x-axis, what is the root, what are the values that in the factored form, where does y equal 0. All of those things are the same. And then this is sort of what I just thought of. Okay, so when a polynomial function is in factored form, the zeros can be determined from the factors, so we just said that. When the factor is repeated n times, we use the term order n. Now again, terminology is not that important to me, but what I am interested in is what that repeating a factor idea does. Okay, so I'm going to do an exponent of 2 here on that. I'm going to take out this one because I want it to still be cubic. So when I look at this now, I have x minus 2 squared, which means if I did expand this, I would have an x squared term times another x. So this is still a cubic function. I still have 3 x's in there. My y-intercept would be negative 2 times negative 2 times 4, which is the 16 that's here. Remembering, of course, that this is exactly the same as having that. So x minus 2 times x minus 2 times x plus 4. What's of interest to me then is what happens at that x minus 2. And so when we look at this point, understanding that it's a double root in that there was x minus 2 there twice, instead of passing through it the way I was earlier on and coming back up at another point, I actually just pass through it and go up immediately. So what I've got at this point right here is essentially the parabola section of that. Okay, so the x minus 2 squared is a parabola. I can zoom in a bit here maybe, or zoom it out a bit. And you see that it's a parabola. And so when we have that as part of a larger expression, we still have essentially a parabola at that point, or at least the parabola influence at that point. We'll look at one here that's a little bit bigger. jump up to the quintics, and just sort of for reference here, I sometimes punch in the y equals part of these, and sometimes I don't. It doesn't really make a difference whether you do or don't. I don't know why I am in this case, or why I did in this case. Okay, so I'm going to hide these other two graphs. And I'll zoom out a little bit. Okay, so what I'm interested in now is what's going to happen with this cube on here. Okay, so we know from the previous example, I have 5 factors. I have 1, 2, 3, 4, 5 x-intercepts. In this case, I essentially have the same thing. I still have 5 x-intercepts. 3 of them happen to be in the same spot. And so again, what's of interest is what happens at that spot. So in this case, I have the x plus 5 factor, which is a negative 5 position, and going through that spot, I have a cubic function. So as we said before, with the previous one, when I had the parabola in there, I had basically a parabolic shape at that specific point. Here I have a cubic function, or cubic shape at that point as well. So there's my cubic function. If I put the other pieces back in, I still have a basic cubic function at that point, and then the rest of the graph continues. It goes up to a certain point. Again, that point is 5 times 5 times 5 times negative 2 times negative 6, and then it drops down through the remaining 2 roots. Sorry, 2, 0. I misclicked there. And probably to no surprise, if I happen to take that a little further and say what happens if I have a 4th power function there, 4th power root, sorry, then I basically have, the basic shape of my quartic function at that point, drops down, comes back up through the last remaining point. Okay, so just finishing up. So hopefully what you take from that is you recognize how important the roots are because they give us points where our graph hits. The y-intercept, of course, can be found by just multiplying out all the constants. And then, what else do we have here? A bit of terminology here again, or a bit of language, I guess, that's not great. The graph of a polynomial function changes sign, and I sort of told people yesterday, don't worry about changes sign. Essentially, what these two things are saying is what we just kind of went through, or this one, sorry, is saying what we just went through. If you have a cube, or if you have a square, then what happens at that point is based on the fact that a squared root, something like x minus 2 squared, the fact that this is a quadratic function means that at the point x equals 2, I get a quadratic function type shape. I get the graph coming up or down, depending on what the rest of the question is, kind of hitting that point and then bouncing back up. If it is a cubic function, then I get the graph kind of coming either down and going through in a cubic shape, or again coming up, and that sort of depends on just what's happened previously or what the rest of the question says. That does remind me of one thing that I missed or didn't state, so I'm going to jump back here fairly quickly. If we have a negative sign in front of anything that we've done so far, and that's maybe not the best example, but what happens is essentially any values that had been positive now become negative, and anything that had been negative now becomes positive. So you sort of see with this red one here, I basically have the same shape, but again starting in the positive areas and dropping down instead of the reverse. So that extra little negative sign out front will give you the idea that our graph is either going to start at the top or start at the bottom based on what the original was. When I look at the cortex, same idea. The basic function starts high, drops down to 0, comes back up. If we make it negative, of course, it starts down low, comes back up. And that should be obvious. The book likes to kind of over-explain this, and maybe I'm even over-explaining it right now. But essentially, whatever was there before is now negative. So if it was a very big number, it's now a big negative number. If it was a negative number because we were talking about cubics and so on, it was negative and now becomes positive. Okay, so the negative sign out front really just does that.